The topic for today is called linearity testing. I'm sure most of you know what the word linear means in a very not, I wouldn't want to say weak sense, but from a very top view. What we are going to check is whether the function is linear or not. I will define all these terms slowly, but this is what we want to do. And this is done in the subject known as property testing. This is an important part of computer science. And this is where we are going to see the application of Fourier expansions, properties of Fourier expansion. And first question, what is property testing? Again, I'm not going into formal definitions of property testing. I will just define formal things for linearity testing and solve it. Property testing is a field which tries to find whether a particular object has a property or not. Okay. I think it's best explained using example. Your object could be a function, or let's say a graph, or a truth table, or anything. And then there are well-known properties. For example, for function, we are going to talk about whether it's a function, is a linear function, it's monotone, it's symmetric, right? There are many natural properties of functions which we can ask. If it's a graph, we can ask, is it connected? Is it triangle free? So on and so forth. Right? The object again is, you are not, sorry, object, but the objective of this field is you are given some kind of a structure or an object. For example, think of a graph, and you want to check if it has a desired property or right. Now, unfortunately, in most of these cases, it is hard to check the property exactly. In the sense that you would actually have to look at the complete object before you can decide whether it has a particular property or not. For example, if you're looking at a graph, right? How is the graph? How will the graph be given to you? By the way, you are all familiar with graphs, right? When I say graphs, it's not the XY axis and things like that, right? You know which graphs I'm talking about. Yes, no? With edges and vertices. Yes. Everyone knows what those graphs are, right?
Yes, sir.
Yes. Anyone who doesn't know what combinatorial graphs are? Okay, good. Yeah. So suppose I want to check whether the graph is connected or not. Now, how will the graph be given to you? Probably, let's say it is given for every edge, you are given whether it is present or not, right? So you are given a string where every string is either 1 or 0. And every bit is either 1 or 0, depicting whether that particular edge is present. And then if you want to check whether the graph is connected, you mostly have to look at the entire edges to figure out whether it is connected. Or let's say if it is triangle free. because it might happen that whatever edge you have not checked, probably that is making the triangle or that is making the graph connected. Right. So what happens is in property testing exactly, we simplify the problem, but then we want the guarantee to be strong. But the running time or the number of queries, so number of queries in the sense what, how much of the object you want to look at, right? How many of the edges you have to see, that in time needs to be significantly. What is simplifying the problem? You will be given the promise that either the object is satisfying a property or far away from the property. Again, what do you mean by far away from the property? It will depend upon the kind of the object. It will depend on what field you are studying. Let's say, for example, in case of finding out whether a graph is triangle free or not, either the graph will be triangle free or there will be at least square root and triangles in the graph. Something like that will be true. So it will not be very, very close to your object, will not be very, very close to it. It will be either satisfying the property or it will be far away from the property. And then you again, with very quickly, by querying by looking at the object at very, very small places with high probability, you want to succeed. What is the new objective or the stronger objective? Succeed with high probability by looking at very small portion of the object. This might almost seem magical, right? Because as we saw for connected and for other things, it seems like we have to see the entire object. But now, if we have the promise and we only want to succeed with high probability, then it turns out that just looking at sometimes constant number of bits, that's good enough for success. Okay, this is what we want to do today, and this is going to be done for the problem of linearity testing. So at least the high level idea of property testing is clear. Questions? Okay, let me give this example and then it might be more clearer. I think, what do I mean by far away and what do I mean by looking at very small portions of the object, right? So let's talk about linearity testing, where my object is a function. What is the property? I want to check whether the function is linear or not. Do you want to guess when is a function linear?
f of x plus y is equal to f of x plus f of y.
Right. So it is called f of x plus y is equal to f of x plus f of y. But now we're in the domain of minus 1 comma 1 to the power n to minus 1 comma 1. So that will be equivalent to what is addition in this domain?
Pointwise
Sorry?
multiplication.
Yes.
f of xy equals fx fy.
Right. Correct. So the first problem, think of it, the first problem would be look at f. F is a Boolean function. Tell me whether for all x comma y pairs is f of xy equal to fx times f. Right. And then what do we want to look at? We want to minimize the number of queries. Okay. You can do whatever you want in the algorithm. I don't care about it computationally. What I want is that whenever you can ask me what is f on some x1, some x2, some x3, but you should minimize those number of queries in the sense that whenever you want to access the function f, whenever you want to find out something about the function f, the only way to do it is through this black box f. You will tell me x, I will tell you x. But every time you do it, I am going to charge you 1 rupee. Definitely, you want to make the cost as small as possible. Once you get the value of f of x, once you get the value of f of y, what you do with it, I don't care. I'm not interested in how much time does it take to process that. What I'm interested in is that you minimize the number of times you ask me the value of function. Suppose it is very, very hard to compute. And then this is the only measure of complexity we are going to. Sounds good? If that is the case, and now if you want to exactly find whether the function is linear or not, how many queries will you take?
Around 4 to the power
Currency
n.
2.
Sorry, around
Sorry, 2 to the power n.
right? Around 2 to the power n, right? Because whatever you have queried, whatever you have not queried, that one I can modify so that the function doesn't remain linear for that particular input, right? And the linearity will, right? That's not a very interesting problem. We will change the problem, again, simplify the problem, but we want a better guarantee. We want the number of queries to be very small. So now, either the function is linear or far away from. This far away from linear will be clear to you in some time. And then only with constant queries you want to succeed with high probability. So this new goal and simplification of the problem is okay.
So in a way, we need 2 to the power n C2 queries, right? Like if we want exactly.
Yeah. So lot of queries. That is what I wanted to. Yeah.
If we have
Whatever is the
queried
number
the
of
value
pairs.
on some x, we can store it, right? So we don't need to
Yeah,
query that
exactly.
x again.
Exactly.
Okay. Yeah.
You don't have to query it every time. Yeah. Very nice. Yeah. So 2 to the power n, but the point is that this is very, very big. And that is not what we want. We only have constant queries to f. Still, we want to figure out with high. Okay. So there are two simplifications. What are the two simplifications of the function? What are the two simplifications? Someone will tell me, how have I made the problem easy?
First, that is the function has to be linear or far away. So far away notion, we have to decide what's that, but and
yes,
that's first constraint. And secondly, we do not want an exact solution. We want it with high probability.
very good. Who was this?
Debarshu?
Devanshu. Thank you. Thank you, Devanshu. Very good. Very good. So these are the two ways in which I have simplified your task. First, I have promised you that either the function is linear or far away from linear. I will explain again far away from linear, but that's one promise. And second thing, I don't want you to succeed with every time. I just want you to succeed with that. How have I made your life difficult?
Still not defined far away.
Yeah, I will. No. No. In the, yes.
Constant. Yeah.
Sorry?
Constant.
Constant.
Constant. Constant.
Yeah.
Yes. Right? That you have to do it in constant. So it seems magical, no? That just by querying like twice, thrice, or let's say 10 times, you will figure out whether the function is linear. Does it seem magical or it doesn't? Okay. Okay. At least when I saw it first time, it was kind of surprising to me. But yeah, the first thing you are annoyed by is what does it mean that the function is far away from? For that, let me look at the definition of linearity first. Right? What are linear functions which satisfy this condition? Fx is equal to Fy for all x comma. Do you know of any linear functions? Is all linear, by the way?
All the characters, I mean the parity functions are linear.
Right. Is all linear? You can easily show it.
No.
No, or is not linear. You can easily show. Okay. Just pick randomly two inputs. One of them is 1, one of them is -1, and then you will see that. That I will leave it as an exercise. But as already pointed out, that these are linear for all. If I pick any partial parity, my elements of my basis, these are going to be linear because I know that chi s of xy, actually this was told to you that this is some very special about these parities. That's why they are called characters. This always. Now, my claim is that partial parities are the only linear. Okay. Sounds good. The obviously you don't know the proof, but the claim is clear, right? We know that all the partial parities are linear. We are claiming that these are the only linear. Just by show of hands, how many people agree? How many people believe the claim? Okay. Okay. Vit and Vatsal. No one else? Anindya also. Okay. Yeah. So this claim is actually correct. Proof is given as an exercise. If I have some time left after today's class, I will try to tell you few ideas how you can prove. But it is given as an assignment in the lecture. Okay. But now you know two definitions of a function being. What are the two definitions? One is that It satisfies the linearity property for all xy. What is the second definition?
It can be expressed as sum of xi's in all the set.
It is
in the set.
equal to chi-sx for some x, right? That is what you want to say. Right? Because these are the only linear functions. This is another definition. We have shown that these two are equal. We have not shown that, but this if you do this exercise, then you would have shown that these two definitions are exact. Udit, were you saying the same definition or you had a different definition in mind? Udit? Someone was saying this sum of xi or something.
I was saying the product basically chi-sx expansion.
Which is the same thing, right? So, right? You agree?
Yes.
Yeah. Okay. So these two are the definitions of a function being linear. And now we want to define what does it mean by far away from linear. You want to take a guess? What would be far away from linear? What should far away from linear should be defined?
The number of terms.
There are just
polynomial
many pairs.
representation is high.
Sorry. Before Udit, there was someone else.
The number of terms in the polynomial representation is high.
Sorry, the number of?
The number of terms in the polynomial representation is high.
Okay. Okay. Definition 1. Number of terms in polynomial representation. Okay. Anything else? Udit, you had something in mind?
I was saying that there are just many the pairs which does not satisfy the linearity property.
Okay. There exist many. Okay.
It's not equal to.
Not. Yeah. Okay. I'm going to take a definition 3, but I will show that definition 2 and definition 3 are going to be equivalent. That is going to be the proof. But definition 3 is saying that for all s, fx is equal to chi-sx only for a constant fraction of x. Let's call this constant fraction 2 by. Let's start with 2 by. Okay? That number is not very, very important. Let's start. Or only or at most. So fx is equal to chi-sx at most on 2 by 3 inputs. We know that linear functions are chi-sx. If I look at all my Boolean functions.
Wait, just a second. Are you saying this for all s?
Yes.
I mean, if f is equal to just one particular chi s naught x, then why are we expecting it to be equal to all chi s x?
No. Sorry. For all s is over this.
You're saying that the definition of a highly non-linear function is for all. So, if f was a linear function, then it would still follow this definition, right?
No. That's why I
Probably.
put a bracket now, right? If my bracket was if I was saying at most for a constant fraction of inputs for all s,
Oh,
fx
for
is
all
equal
s.
to fx.
Okay.
That is why I'm putting the bracket.
Okay,
So
got it.
on no s, fx agrees with chi-sx on a large fraction. Right? So other way to say it is on no s, f agrees with chi-s on a large fraction. This makes more sense? both of these are equal, right? So this is the set of this rectangle is the set of all Boolean functions. Linear functions are these chi-s's. I agree there are different ways in which you can define what does it mean to be far away from here. We are going to take definition 3 and we are going to show that it is equivalent to definition 2. But anyway, let's not worry about it now. Why is it showing the equivalence? But let's consider 3. And I'm sure that you can find it one of the natural ways to define far away. Right? So f is far away from linear if you look at the distance between f and chi-s, it is pretty big. The number of places where f and chi-s agree, that is small. So f comma chi-x. Okay. Again, I'm not saying that definition 1 and definition 2 are not valid definitions. Definition 2 definitely is equal to definition 3. And even definition 1 is valid. What we are going to worry about is definition 3. Does the definition 3 sound natural to you? That's okay. Should we move ahead?
Yes.
Yes. Okay. So now fx is equal to chi-sx at most for a constant fraction of input 2 by 3. You know that either function is linear or fx is equal to chi-sx. And now you want to check whether the function is linear or not. Right? The algo is going to be very, very simple. Do you want to take a guess on what the algorithm is? Especially knowing that definition 2 and definition 3 are equivalent.
We'll query f on 3 inputs and check by comparing the pairs.
Right. The simple thing would be pick x comma y at random, check whether fxy is equal to fx times fy or not. If this is satisfied, we will say the function is linear. If it doesn't get satisfied, we will say that function is not. That's all. Very, very simple
So we are
algorithm.
essentially just checking one pair. That's it.
Yes. So I will show you that if you want to increase the success probability, you can do it for more pairs, but only for constant fraction of pairs, it will be good. Only for constant number of pairs, that will be good. It depends on how high the probability of success you want. Okay. But at least at this point, let's start with just checking one. I'm saying you check it for 1 or 2 or 3 pairs. That's good. So, any questions about the algorithm? No, right? So then tell me, to prove its correctness, what do I need to prove? If I want to prove that my algorithm works correctly, then what do I need to?
So like we need to show some error rate.
Then,
Yeah. So if function is linear, if f is linear, then our algorithm has 0% error rate.
Very good. If f is linear, then algo will also say that f is linear, right? This is very clear. Now, if f is not linear, then we also know that it is far away from. Then what do we want to say? With high probability, algo says non-linear, correct? What does this mean? Given the algorithm description, what does it mean?
With high probability, the pair that we have chosen would disagree.
Right. And since I'm choosing it uniformly, I want to say that for constant fraction of pairs fx times fy is not equal to fx. Do you agree that if I show this, if I show that for, let's say, I have 100 pairs of x comma y, if for 90 of those pairs fx times fy is not equal to f of x y, then my algorithm will succeed with high. Right? So this is what I want to show, that for most of the pairs, this linear condition will not be satisfied. Most means whatever probability you want to succeed. You want to succeed with 2/3 probability, then 2/3 fraction of pairs should not have linearity condition satisfied. Right? That's the exact meaning of saying that algo says not. Right? That sounds good. Have I confused you? Please, if I've confused you, please tell me. We can, or say, yes, we are fine, then I can move on.
Yes, fine.
Fine. Anyone who is not fine with this? Okay. So remember what we are trying to.
When you have written here constant fraction of pairs, hello?
Yes.
So when we have written here constant fraction of pairs, what exactly do you mean? Is that a high fraction or a low fraction? I mean, you said here it's a high fraction, but I think a few pages back you used it to mean a low fraction or something.
No. For here, I want to say that for at least some constant fraction of.
Okay.
Does that make it clear? Right? Because if that happens, then at least with that probability, if for at least half fraction of the pairs, fx times fy is not equal to f of xy, then my algorithm will answer correctly with probability at least half. Right? Other way to say it is, for at most some constant fraction of pairs, f of x times f of y is equal to f of x, which is the same.
Okay, got it.
Got it? Good. Yeah. So we had two definitions of linearity. One was f of xy is equal to f of x times f of y for all x comma y. This was one definition of linearity. What was the other definition of linearity? Aditya, can you tell me what was the other definition of linearity?
fx is chi s x for some s.
For some s. Right? These were the two definitions. And then now, in some sense, we have a weaker version of these. We have a robust version of these definitions, which we want to be. We want to say that if for most of the, if for some constant fraction of the inputs, for at least some constant fraction of the inputs, fx is not equal to chi sx. If for at least constant fraction fx is not equal to chi sx, again this is for any s, fx is not close to chi sx, this is same as for at least a constant fraction f of xy is not equal to f of x times. Right? So the statement which we want to prove is in some sense a direct generalization of the equality we have seen before. If it is clear to all of you what we want to prove, then we can start. Any questions about this? This is clear. Our task is clear.
So I have this question about
So
how
the-
will go the how do we show this equivalence, the second equivalence? Like if there is if f of x does not agree with chi-s of x on some x, that but still might happen that f of x y for some y is equal. I mean, if for two x and y, if f of x not equal to chi-s of x and f of y is not equal to chi-s of y, it must still happen that f of x y is the same as.
Sorry. Can you repeat? I didn't get your question. Are you asking how are we going to prove it, or you are saying that this cannot be true?
I mean, if we try to understand it, so I was trying to see if for all the pairs where f of x does not agree with some chi-s of x, so I mean, then those pairs would be included in the right side. So
No.
that wasn't.
That is not how it is going to happen. It is
Yes.
because what will happen is if you pick an x where it agrees with chi-s x, and if you pick a pair which is another x where it does not agree, then the linearity might be satisfied, might not satisfied. So it is very weird, right? You don't know whether on xy whether they will agree or not. Right? On x, fx is not equal to chi-s x. On y, fy is equal to or not equal to chi-s y. You don't know whether f of xy that it agrees with chi-s of xy or not. So that depends on how you have lined it. And that's why it's a difficult problem. That argument is not going to work. And I will show you a beautiful argument using Fourier analysis, which will work. That's the whole point of this. Okay. So such arguments will not. Okay. Problem is clear. What we want to show now? Should we go ahead? Obviously, you are going to help me out with the proof. Let me just write. Yes.
In the previous page, f of x is not equal to chi-sx for at least a constant fraction for any s. For any s.
Yes.
Okay.
That is. Yes.
Okay.
Yes. Let f be a Boolean function such that for any s, fx is not equal to chi-sx for at least 1/3 fraction. Okay. So at least on third of the inputs, fx does not agree with chi-sx. That is the definition of the f to be far from linear. Then we want to show then for at least a constant fraction. Now this would be 2/3. Input pairs x comma y, where x and y are independently and randomly chosen and uniformly chosen from 2 to the power. Right? Then for at least a constant fraction of input pairs x comma y, f of xy is not equal to f of x. Okay. Sounds good? Are you clear that this is the theorem which you want to prove to show that our algorithm works?
So in the theorem, you said that 1/3 maps to 2/3. So what's the mapping?
That we will also do, but that mapping is not really important, right? Because even if we go from constant fraction of inputs to some constant, see, and so this repetition of algorithm I will talk about, but this, what does this say? This is saying that my algorithm succeeds with probability 2/3.
Yes.
Correct. Now, if I want to make this 2 by 3 to, let's say, 99 by 100, what I would do is, instead of doing my algorithm 1 times, I will do it 100 times. That will, the number of queries done will still remain constant. It will become 100 times constant, but it will still remain constant.
Yes, yes, yeah.
But the probability of success will become really, really small. We will do that calculation once I prove this. Okay.
Yeah.
So that's why this mapping is not that important. I will go show you the exact mapping also, but the exact mapping is not that important. Okay.
Yes.
Okay. Let's go through the proof. Right? We want to figure out how many fraction of input pairs fxy is not equal to f of x, f of y. That means I want to relate with this quantity, right? So if f of xy is not equal to f of x, f of y, then what will be this quantity? F of x times f of y, f of xy.
-1.
Good. If f of xy is equal to f of x times f of y, then this quantity would be
1.
That is clear to everyone, right? These are plus minus 1 variables, right? The output is plus minus 1. So if 1 is minus 1, 1 is 1, then their multiplication will be minus 1 otherwise. How can I convert into a 0, 1 variable?
Replaced by plus, I guess that's something.
Sorry, replaced by?
Plus, I mean, you are talking about 0, 1 variable, right? So,
Right. So I want to have 1 if f of xy is not equal to f of x, f of y, and I want to have 0 when f of xy is equal to f of x.
That would be 1 minus f of x, f of y, f of x by 2.
We take XOR. F of x XOR, F of y XOR, F of x.
See, again, when you're thinking of XOR, you are thinking of 0, 1 variables, no?
Yeah.
Right? So do you agree that this will do the trick? Actually, in this case,
So,
okay.
so F is outputting -1 and 1, right?
Yes. F is outputting
Yeah,
minus
yeah,
1, 1.
this will do.
So, okay, this quantity will be 1 if f of x times f of y is equal to f of xy and 0 otherwise, right? This you agree, correct?
Yes.
Right. So when function is far away from linear, the expected value of this quantity is actually my failure curve. Right? I can, as Aditya said, as Udit said, I could have taken it to be half minus half, then it would be my success curve. Right? But I'm just, for the ease, finally I have to worry about this quantity. So let's stay with me and let's say this is my failure curve. Okay, does that sound good? That is fine, right? This is the quantity which I want to calculate. Right? This half plus half fx, fy, fxy tells me whether I succeed on a particular pair. If I take the expectation over all x comma y, it will tell me my probability of whether, since it is a uniform and independent picking of x comma y, this will give me the probability with which I succeed or I fail. Right? So this is the quantity I want to calculate. Are there any questions about why I am calculating this quantity? Anindya, Vatsal, are we okay?
Yes, sir.
Okay. So let's do this. Let's calculate this. Okay, this is okay. Why can I write this?
Linearity of expectation.
Good. What is the next step? Can I simplify? Can I take my expectation of y inside?
We can write f of x as f of xy times f of y. Can we do that?
No, we don't know. F is far away from linear, right? So we don't know whether f of xy is equal
Right,
to
right,
f of
right.
xy.
Sorry.
Yeah. We want to take the expectation of y inside. And clearly, since y is independent of x, I can take f of x outside. Right? This is because think of it as if you had written it as summation, you can take f of x outside in the summation. That's all. Sounds good? Okay. Now, what do I know about this? Does this seem familiar to you?
It is the inner product of
Convolution, I guess.
No, it is not the inner product. It is actually the convolution.
yes.
Right? Remember what are we doing? We are expectation over y, fy multiplied by f of xy. This is convolution of f with this is convolution of f with
Itself.
itself. Yes. This is f star f. If you look at the definition of convolution, this is exactly the definition. This means what I'm interested in is I've gotten rid of one variable, which is good for it. Okay, now looking at this, you should be very happy. Why should you be happy? What is the reason for your happiness?
Entire thing is function of x.
That is true. That was the first cause of happiness. I'm asking now what is the cause of happiness? Remember, you are a champion in Fourier work.
Because now as you know that I mean the convolution basically you can separate the Fourier terms and multiply.
Not now. In convolution you can, but that we will do one step later. But what is this? The thing which I have highlighted now.
I mean
Inner-
it's
inner-
f hat
inner
of phi.
product.
I mean phi.
Yes.
Inner product of
Yes.
both the functions
Yes.
in terms of
the cause of my happiness is Planck-Schnell's theorem. Correct? This is equal to half plus half summation over s f hat of s, whatever is this convolution, s. Sounds good? And now, as already pointed out, we know what this quantity is. What is this quantity?
F hat of s into f hat.
Sorry?
F hat has into f hat has.
F hat s square, right? Yeah. This is equal to half plus half summation f at s. Sounds good?
Q.
Sorry, cube, yeah, cube. Very good. Right? And now you can already see. So most of the time, our task would be to convert our problem into Fourier domain, and then things will become. And now look at this. If f was equal to chi s, then what will happen?
This summation should be 1.
Right. What will f at s cube summation s f at s cube will be? Only one of the Fourier expansion will be, one of the Fourier coefficient will be 1, everything else will be 0. This quantity, if f of x was equal to chi sx, what will be this quantity?
1.
This
1.
will be just 1. Right. But if all my Fourier coefficients were small, and then if I take their cube and add them up, they will become really, really small. Small. This quantity will become small. Do you agree? Right? If half plus half is equal to 1, if I take the cube, it will become 1 by 8 plus 1 by 8. Right? So if my Fourier coefficients, the weight was well distributed, then this quantity will become smaller and smaller. Right? And why should f at s be small?
Because for a large number of SS, f hat s would be non-zero, and the summation over s f hat s square should be 1.
No. Now I'm asking why f at s has to be small. If f at s are small, then the summation as f at s cube will be small. That I agree.
I mean, the summation of f hat s square is bound by 1 because that has to be the norm,
Mhm.
and there would be a large number of s such that f hat s is non-zero. So that is why each of them should have a small modulus.
Why should there be lot of them which have small modulus?
I mean, the large number is by because they none of them is too close to. I mean, so the function is not too close to any of those chi
Exactly.
sx.
They are far away from chi-s. F is far away from chi-s. That's the reason. Right? Okay. We will remember that our failure probability is half plus half summation f at s. This I can write
Sir,
as
if we try to make f at s such that this summation is close to 0, then that would still make the probability of around failure around half. So I mean, should we try to make it more negative, probably?
no. Again, my failure probability of half, I'm very, very happy
Okay, yeah.
because I can change half to 99 by 100 very, very easy.
Oh,
I
by
just
multiplying
want my
it.
failure probability to be less than 1 by a constant. Even if
Okay,
my failure probability is 1 minus 1 by 100, I'm very, very happy. And I will show you why. Okay. So this sounds good. I can always instead of 1 f at s, I can change it with maximum. Then my failure probability will only increase. Right? What is this?
1.
Right. This is half plus half max as f. Okay. Now I just want to say that all my f at s's are small. And how will I prove it? because I know that f is far away from any time. Now, if fx is not equal to chi sx on 1/3 fraction of inputs, what can I say about fx?
It would be maximum 1/3
Why?
because we can write f hat as the inner product of f and chi s, and so it will be 1/2 power n summation over x fx times chi sx, and when they agree it gives a 1, and when they disagree it gives a -1. So they're disagreeing on at least 1/3 inputs. So there are about 2/3 ones and 1/3 -1s. So
Exactly. Very good. So I know that might be easier for you to think of it in terms of summation. You can definitely convince yourself with summation, but think of it in terms of expectation also, right? As you said, for 2/3 fractions, this will give me 1. That will give me at most 2/3. And then I will get -1 for at least 1/3 fraction. With 2/3 probability, I will get +1 with at most 2/3 probability. I will get -1 with probability at least 1/3.
yeah,
That's why this expectation value is going to be less than 1. So my failure probability is less than 1/3. Sorry, 2/3. That means my success probability of my algorithm is 1/3. So I should do a small change in my theorem. I should say that for at least 1/3 fraction of inputs, this does not. And if you want to make this exact, you can say that if for epsilon fraction of inputs fx is not equal to chi sx, then for epsilon fraction of inputs this thing will not. So the mapping is actually very, very clear. What will happen if for epsilon fraction of inputs fx is not equal to chi sx, then your f at s will be less than 1 minus 2 epsilon. And then your failure probability is equal to half plus half 1 minus 2 epsilon, which is equal to 1 minus epsilon. That means your success probability is going to be epsilon. Again, this is not very important. You can do these calculations later. Okay, I've taken 1/3 and I've gotten 1/3 probability of success. You can change it to anything and you will get the correct success probability. For epsilon fraction where fx is not equal to chi sx, your success probability will also be epsilon. You can check that. This is true if we had taken only one pair. Okay, so let me just do the last thing, which is how to amplify success probability. Right? Suppose we succeed with probability 1/3. We have an algorithm. This is actually true for any randomized effect. If we succeed with probability 1/3 and it is a one-sided algorithm. What do I mean by one-sided algorithm? If f was linear, then we always outputted linear. There was no error on one side. Correct? This was true for this algorithm. If f was linear, we always outputted linear. And then if f is non-linear, or sorry, far from linear, then we succeed with probability 1/3. But this 1 by 3 you don't like. You want to make that you succeed with probability, let's say 99 by 100. How do you do this? What would be your idea? I think it's a very, very natural way.
We can make multiple queries, and then in order to find out the success probability, we'll calculate the probability of the binomial distribution to be always one.
No. It need not be very, very complicated. This is a one-sided algorithm, right? So we are just going to repeat the algorithm independently.
Yeah,
Let's
I
say
was
10
just
times.
telling how to calculate the new success probability.
Yeah, you don't have to worry about actually binomial. The binomial you have to worry about when it's a two-sided error. So you do this majority kind of thing. But here it is not required. If you repeat the algo 10 times, then and at any point you get a pair such that f of xy is not equal to f of x, right? So you have what does it mean in this case when you repeat the algo 10 times? You have chosen 10 pairs, and for each of the pair you are checking whether f of xy is equal to f of x times f of y or not, right? So if there exists any pair out of 10 for which fx times fy is not equal to f of xy, then I know that the function is not. Agree? Other way to say it is, if all the time my function says, if any time my function says far from linear, then I'm 100% sure that the function is far from linear. Another way, if f is linear, then my algo will always output linear. You can check as many pairs as you like. F of x times f of y will always be equal to, right? I will say that my algo will say that f is. Okay. Now, what is the probability if the function was far from linear? What is the probability that it outputs linear? This is a simple math question for 12th class or something.
2 by 3 to the power 10.
Right. So the success probability, so the failure probability is one pair failure probability was 2 by 3, but now for all the 10 pairs, the thing my algorithm should fail. That will happen with probability 2 by 3 to the power 10. So then my success probability is 1 minus 2 by 3 to the power 10. And you see how small this is, right? You can calculate. I do I want to do 0.6. Let me just do it in a calculator and I will tell you. Okay, so even if I had repeated 8 times, this success probability will become 0.9. Okay, so my success probability goes very, very quickly by just repeating the algorithm few times. That's why I said that even if my success probability is some small constant, I am happy. I don't care what that exact constant is. But the crux of the argument was the statement that if my function was far from linear, or fx was not equal to chi sx for at least 1 by 3 fraction of inputs, then for at least 1 by 3 fraction of inputs, fxy will not be equal to fx times. And the proof required simple manipulation of Fourier coefficients. We frame our problem in terms of f, convert it into Fourier domain, and as soon as we convert it into Fourier domain, the answer. This gives the famous BLR algorithm. Blum, Luby, and Robinfeld's linearity testing. The famous algorithm.
So are there